In the 17th century, the world of science was ruled by certainty. The heavens, once thought to move according to divine design, began to obey equations written by human minds. When Isaac Newton published his law of universal gravitation, he united the fall of an apple and the orbit of the moon under a single principle. Every mass in the universe, he proposed, attracts every other mass with a force that weakens with distance but never disappears entirely. It was a law of astonishing reach, one that seemed to weave the cosmos together with an invisible thread of attraction. To Newton and his contemporaries, this was a triumph of reason. With a few symbols, he could explain the tides, predict eclipses, and describe the dance of planets around the sun. The universe appeared mechanical, precise, and comprehensible. If one knew the positions and velocities of all things, one could, in theory, predict the future and reconstruct the past. It was a vision of cosmic order where everything, from falling raindrops to the paths of comets, followed predictable rules. But even as he changed history, Newton was troubled by what he had created. He had discovered how gravity worked, not why it worked. What was this mysterious force that reached across the emptiness of space? How could one planet feel the pull of another across vast distances, with no substance connecting them? Newton called the notion of action at a distance absurd, even as his equations required it. He could describe gravity's behavior perfectly, yet he could not explain its cause. For nearly 2 centuries, physicists accepted this mystery. Newton's laws worked so well that few dared question them. Astronomers used them to chart the solar system with breathtaking precision. The moon's motion, the orbit of Venus, the return of Halley's comet, all unfolded exactly as the equations foretold. To the human mind, the universe appeared complete. Yet the cracks in this perfect picture began to show. When astronomers measured the orbit of Mercury with increasing accuracy, they found that its closest point to the sun slowly shifted over time, a precession that Newton's theory could not fully account for. The discrepancy was tiny, only a few arcseconds per century, but it persisted. Scientists proposed that perhaps an unseen planet, named Vulcan, circled close to the sun and tugged on Mercury's orbit. But no such planet was ever found. The mystery lingered like a small shadow on Newton's shining edifice. By the late 19th century, other questions were emerging. Experiments suggested that light behaved strangely, not as a simple wave moving through space, but as something deeper. In 1887, Albert Michelson and Edward Morley sought to detect Earth's motion through the so-called ether. The invisible medium scientists believed carried light waves. They expected to see differences in the speed of light depending on direction. But the result was shocking. There was no difference at all. Light's speed was the same no matter how Earth moved. The ether, it seemed, did not exist. This result did not fit the Newtonian world. If space were merely an empty backdrop and time flowed uniformly everywhere, how could the speed of light remain constant for all observers? The foundations of classical physics trembled. Something about reality itself, about motion, distance, and time, was not as it seemed. Amid this quiet revolution, a young man named Albert Einstein was working in a patent office in Bern, reviewing technical applications by day and pondering the nature of the universe by night. Unlike most physicists, he was not constrained by formal laboratories or academic expectations. His curiosity was guided by thought experiments, vivid mental pictures of riding alongside beams of light or falling freely through space. He wondered whether the key to understanding the universe lay not in forces, but in perception. Einstein admired Newton's genius, but doubted his framework. He sensed that gravity, the most familiar of forces, might be an illusion born from deeper geometry. If light speed was constant, perhaps space and time themselves were not fixed but flexible, stretching and compressing depending on how one moved. The idea was radical, yet elegant. What if gravity was not a pull through emptiness, but the shape of space itself? Einstein's early work on special relativity in 1905 provided a clue. It showed that space and time were not independent entities, but part of a single continuum, spacetime, in which the motion of light remained constant for all observers. Time could slow down, lengths could contract, and simultaneity itself could differ from one observer to another. But special relativity dealt only with uniform motion. It had no place for acceleration or gravity. To reconcile those, Einstein would have to rebuild physics once again. Still, a question lingered in his mind. If motion and acceleration could alter the experience of time, could gravity and acceleration be the same thing? What we called weight, the feeling of being pressed into the ground, might not be the result of a force at all, but resistance to free fall. Perhaps the apple that Newton saw falling was not being pulled by an invisible hand, but was following the natural curve of spacetime itself. These ideas were not yet formalized, but they carried an extraordinary simplicity. Einstein imagined that gravity might not be a fundamental force, but a property of geometry. Matter tells space how to curve, and curved space tells matter how to move. The apparent pull of gravity would then be a misunderstanding, a reflection of the shape of the universe, rather than an action between masses. This insight, still forming in Einstein's mind, would soon transform physics. It would explain Mercury's wandering orbit, the bending of starlight, and the slow ticking of clocks near massive bodies. But before those revelations, Einstein needed a way to prove that acceleration and gravity were not two separate phenomena, but one and the same experience of curved spacetime. To understand his breakthrough, we must first understand how motion, time, and light are connected. Einstein often said that the greatest moments of insight come not from complicated experiments, but from simple imagination. One such moment arrived when he pictured himself inside a small elevator sealed away from the outside world. In that isolated space, he asked a question that would overturn the understanding of gravity itself. What would he feel if the elevator were floating freely in space, far from any planet? He realized that in such a condition, if he let go of an object beside him, it would float weightless. Both he and the object would move together, falling at the same rate through space. There would be no sensation of weight, no force pushing him to the floor. Then, he imagined the elevator accelerating upward in deep space, far from any stars or planets. Suddenly, the floor would press against his feet, and a dropped object would fall toward the ground, exactly as if the elevator were standing still on Earth. The two situations, one caused by gravity, the other by acceleration, felt identical. Einstein concluded that no experiment inside the elevator could distinguish between them. This was his principle of equivalence, a concept that would become the cornerstone of his theory of general relativity. The idea was simple, but its consequences were immense. If a person inside a closed box cannot tell whether they are being pulled by gravity or accelerated by a rocket, then gravity itself may not be a force at all. It may simply be the effect of living in a reference frame that is accelerating through curved spacetime. What Newton had described as attraction could instead be geometry, the shape of the universe guiding motion along natural paths. Einstein's thought experiment echoed the work of earlier thinkers. Galileo had shown that all bodies fall at the same rate regardless of their mass. Whether it was a cannonball or a feather in the absence of air, gravity accelerated them equally. Later, Hungarian physicist Laurent Earphones used delicate torsion balances to test this principle with extraordinary precision, confirming that inertial mass and gravitational mass were indistinguishable within tiny limits of error. Centuries later, Satellites in orbit would repeat those tests with even greater accuracy, proving that this equality was not coincidence, but a fundamental property of nature. For Einstein, the equality of inertial and gravitational mass was the clue that the universe was whispering something deeper. When an object falls freely, it is not being pulled by an invisible hand, but is simply following the straightest possible path through space-time. The reason it appears to accelerate toward the Earth is because space-time itself is curved by the Earth's mass. A freely falling apple feels no force. It is weightless. It is the ground, pushing up to resist free fall, that creates the sensation of gravity we feel. To picture this, Einstein often described how light would behave in an accelerating elevator. Suppose a beam of light entered through a small side window as the elevator accelerated upward. To an outside observer, the light would travel in a straight line, but to someone inside, the beam would appear to bend downward as it crossed the cabin, hitting the opposite wall slightly lower than where it entered. If acceleration and gravity were equivalent, then light must also bend in a gravitational field. This single realization opened a door to one of the most extraordinary predictions in physics, that massive objects could curve the very paths of light itself. It was a radical shift. For centuries, space had been considered an empty stage upon which matter performed. Now, Einstein proposed that the stage was part of the play, flexible, responsive, and alive with structure. He began to see the universe as a web of geometry, where matter and energy could stretch, twist, and warp the very fabric through which everything moved. Mathematically, Einstein found that the key lay in the equality of masses. The inertial mass, which resists acceleration, and the gravitational mass, which determines the strength of gravitational attraction, were exactly the same. This was not a coincidence, but a fundamental symmetry of the cosmos. It meant that gravity was not a distinct interaction like electricity or magnetism. Instead, it was a manifestation of the way space-time responds to energy and mass. As Einstein refined his ideas, he realized that this principle could explain not only the motion of falling objects, but also the behavior of time itself. In an accelerating elevator, clocks near the floor would tick more slowly than those near the ceiling, because the light that carries signals between them would lose a tiny fraction of its energy climbing upward. The same must be true in a gravitational field. Time must flow differently at different heights. Gravity, then, was not only geometry of space, but also the warping of time. At first, this conclusion seemed almost too strange to accept. Time, the one constant by which all experience is measured, could not possibly vary from place to place. Yet the logic of Einstein's reasoning left no alternative. If acceleration and gravity were equivalent, and acceleration could stretch time, then gravity must do so as well. The universe was revealing itself as a place where geometry and motion were inseparable from the flow of time itself. In the years that followed, Einstein worked to express these ideas mathematically. He studied the work of Bernhard Riemann, who had shown that space could be curved rather than flat, and sought a set of equations that could describe that curvature precisely. It was an enormous challenge, one that would occupy him for nearly a decade. But the principle of equivalence gave him a guide. It told him that in any small region of space-time, the laws of physics would look the same for a freely falling observer as for one floating in deep space. This insight would lead him to the general theory of relativity, the geometry of gravity itself. The elegance of the principle was breathtaking. With it, Einstein transformed gravity from an invisible pull into the shape of reality. He showed that when we drop a stone, it does not fall because something draws it downward, but because it follows the natural curve of space-time created by Earth's mass. The same principle explains the orbits of planets, the motions of galaxies, and the bending of starlight across billions of kilometers. The universe, once described by forces acting across distance, became a tapestry of curvature and motion. Every mass shaped the geometry around it, and every motion followed that geometry. Gravity was no longer a force to be explained, but an illusion born from our limited perspective within a curved world. Einstein's elevator thought experiment had done more than resolve Newton's discomfort with action at a distance. It had redefined the nature of space and time. The next step would be to express this vision in mathematical form and to test it against reality. Einstein's search for the mathematical language to describe his vision was not straightforward. He was not primarily a mathematician, yet he understood that only the deepest geometry could express what his intuition told him was true. He turned to the work of Bernhard Riemann, who decades earlier had shown that space need not be flat. Riemann had imagined spaces where lines that seemed straight could curve, where the rules of Euclid failed, and where geometry itself could depend on position. This was exactly the kind of language Einstein needed. He began to imagine matter not as something sitting in space, but as something shaping it. The presence of mass and energy could tell spacetime how to bend, and the curvature of spacetime would tell matter how to move. The planets, he realized, did not orbit the sun because they were pulled by an invisible force. They were simply following the straightest possible paths through a warped geometry. These paths, called geodesics, were straight only in the context of curved space. The illusion of a pull came from our human tendency to imagine flatness where none existed. To make this concept real, Einstein spent years developing a set of equations that could relate matter and energy to curvature. He needed a mathematical structure that could describe how space-time itself could change, stretch, and ripple. Working mostly alone, he built upon Riemann's geometry and the tensor calculus developed by Gregorio Ricci and Tullio Levi-Civita. It was one of the most difficult journeys of his life. He would later say that the math nearly defeated him. But by 1915, he succeeded. Einstein's field equations were simple in form, but infinite in meaning. On one side, they described the curvature of space-time, a set of terms representing the geometry of the universe. On the other, they described the energy and momentum of matter and radiation. The two sides were equal, bound by the elegant statement that energy and mass shape the geometry of space-time, and geometry dictates the motion of energy and mass. It was a closed loop of cause and effect, a universe that shaped itself. When Einstein presented these equations to the Prussian Academy of Sciences, the implications were staggering. The cosmos, he said, was not a static stage upon which matter moved, but a dynamic entity that could stretch, twist, and fold. Even light, which always moved in straight lines through space-time, would appear to curve near massive objects because the space it moved through was curved. Suddenly, Newton's action at a distance was no longer mysterious. There was no invisible hand pulling on the planets, only geometry guiding their motion. To visualize this, imagine a marble rolling across a stretched rubber sheet. If the sheet is flat, the marble moves straight. But if you place a heavy ball in the center, the sheet bends, and the marble's path curves naturally around the depression. Nothing pulls it sideways. It is simply following the straightest possible line on a curved surface. Now imagine that sheet extended into 4 dimensions, 3 of space and 1 of time. That is Einstein's universe. At first, his ideas were met with skepticism. Newton's law had explained the heavens for centuries. Many physicists doubted that geometry could replace the certainty of force. But Einstein was not guessing. His theory made predictions that could be tested. One of them was that light passing near a massive object, such as the sun, would bend by a specific angle, twice as much as Newton's laws predicted. Another was that time itself would slow down near strong gravitational fields. These were not philosophical speculations, but measurable consequences of his equations. The first hint of validation came from an old mystery: the precession of Mercury's orbit. When Einstein applied his equations to the problem, the tiny discrepancy that had puzzled astronomers for decades vanished. His theory predicted exactly the observed motion. For the first time, Newton's framework had been surpassed not by correction, but by replacement. Einstein was both exhilarated and cautious. A single solved anomaly could not prove such a radical idea. He knew that only direct, independent confirmation could elevate his theory from beautiful mathematics to physical truth. That confirmation would come from the sky itself, during a moment when the sun would briefly reveal whether space truly bends. The world was not yet ready for the idea that gravity was geometry. It was 1915, and Europe was deep in the chaos of war. Few had the time or means to test his predictions. Yet Einstein waited, confident that nature would one day show the truth. His vision had transformed the understanding of gravity from a force that reached across emptiness to a property of space-time itself. The illusion of attraction was gone. In its place stood a deeper harmony between matter and geometry. The implications were vast. If space could curve, could it also ripple? If geometry could bend under the influence of matter, could it carry waves like a pond disturbed by a stone? The questions would linger for years, but Einstein already sensed their answers. His theory described not a static cosmos, but a living one, in which space and time were as dynamic as the stars themselves. As his equations spread across the scientific world, one prediction stood above all others. During a total solar eclipse, the sun's gravity should deflect the light of distant stars, shifting their apparent positions in the sky. If such bending were seen, it would prove that light, the most incorporeal thing known, could be curved by gravity's geometry. The opportunity would come in 1919, when the moon would pass directly in front of the sun, and the stars near its edge could be seen. A team of astronomers, led by Arthur Eddington, would travel across oceans to capture that fleeting moment and measure whether Einstein's impossible idea was true. Light, the purest messenger of the universe, was about to reveal whether space itself could bend. To prove that gravity is geometry, nature would have to bend light, shift time, and move stars accordingly. In the early years of the 20th century, Einstein's imagination was consumed by one question: what truly causes the sensation we call gravity? He had already shown in his theory of special relativity that motion could alter time and distance, but gravity still stood apart, a strange and familiar force that seemed to pull on everything without touch or medium. To Einstein, this separation made no sense. Nature, he believed, could not operate through disconnected laws. The path to unification began with a simple, yet profound thought. The experience of gravity and the experience of acceleration might be one and the same. He often explained this using his now famous elevator experiment. Imagine a person sealed in a small windowless elevator, floating in deep space, far from any stars or planets. If they release a ball from their hand, it will remain beside them, drifting peacefully. There is no sense of up or down, no weight, no fall, only stillness. Now imagine the elevator begins to accelerate upward through space, pushed by a rocket. Suddenly, the person feels their feet pressed against the floor. When they release the ball again, it falls to the ground. To them, it appears as though a gravitational force has returned. But in truth, there is no planet nearby, no massive body pulling the ball downward. The feeling of gravity has been created entirely by acceleration. Einstein realized that this was not an illusion. It was a clue to the nature of reality. The laws of physics inside that accelerating elevator would be indistinguishable from those inside a stationary room resting on Earth's surface. The two experiences were equivalent. Gravity and acceleration could be two descriptions of the same phenomenon. This was the principle of equivalence, and it would become the heart of his general theory of relativity. The principle connected centuries of observation. Galileo had already demonstrated in the 17th century that all objects fall at the same rate, regardless of mass. If one drops a stone and a cannonball from the same height and removes air resistance, they hit the ground together. This equality seemed mysterious. Why should heavy and light objects fall alike? Newton himself had recognized this equality between inertial mass, which measures resistance to acceleration, and gravitational mass, which measures response to gravity. Yet he treated it as coincidence, not cause. Einstein saw it as the universe's deepest clue. If inertial mass and gravitational mass are truly identical, then the motion of any object under gravity should be indistinguishable from its motion in free fall. The apple that seems to be pulled toward the ground is, in fact, following the natural curve of spacetime. It feels no force at all. The only thing that creates the sensation of weight is the ground pushing up, preventing free fall. Standing still on Earth is not the absence of motion, but the constant experience of acceleration upward through curved spacetime. To Einstein, this inversion of perspective was revolutionary. What we feel as gravity might not be a real force acting on us, but the result of living in a universe whose geometry dictates how things move. If acceleration and gravity are the same, then the distinction between a rocket's thrust and Earth's pull vanishes. Both are simply different manifestations of motion through spacetime's curvature. He tested this reasoning through imagination and mathematics alike. Suppose, he thought, a beam of light entered an accelerating elevator. To an outside observer, the light would travel straight. But to the person inside, the beam would appear to curve downward as the elevator moved upward beneath it. If acceleration and gravity were equivalent, the same bending must occur when light passes near a massive body. Gravity must bend light, not because light has weight, but because the path it follows through curved spacetime is itself bent. This realization was astonishing. Light, once believed to move in perfect straight lines, would now reveal the curvature of the universe. The bending of light would no longer be metaphor, but measurement. In the coming years, this prediction would lead to one of the most dramatic experiments in the history of science. But first, Einstein needed to establish a solid foundation for his idea. Experiments on Earth already supported him. Hungarian physicist Laurent Earphones had used a delicate torsion balance to test whether objects of different materials fall at the same rate. His experiments, performed with extraordinary precision, confirmed that the equivalence between gravitational and inertial mass held true to within 1 part in 100 million. This meant that nature itself behaved exactly as Einstein's elevator required. All masses, regardless of composition, experience gravity in the same way. Centuries later, satellites orbiting Earth would extend those tests even further. In space, engineers sent instruments designed to measure the tiniest differences in acceleration between materials. Each result reinforced the same conclusion. The principle of equivalence was real. Gravity could indeed be reinterpreted as the geometry of motion rather than the action of a force. Einstein's insight now demanded a new mathematical description of the universe. If gravity was not a pull, then the equations of Newton could no longer apply. Instead, space-time itself must possess a shape that changes in response to mass and energy. Objects move along the straightest paths available in that curved geometry, and those paths appear to us as the effects of gravity. This was a bold departure from everything physics had believed for centuries. But Einstein's reasoning was simple. If every observer in freefall experiences weightlessness, then freefall must be the natural state of motion. The floor beneath our feet exerts an upward acceleration that interrupts that state, creating what we perceive as gravitational force. Gravity, then, is not a true interaction between masses, but a manifestation of spacetime's curvature influencing motion. Mathematically, this meant that the equality of inertial and gravitational mass pointed toward a geometry rather than a force law. Instead of describing attraction between two objects, Einstein would describe how matter curves space-time, and how curved space-time tells matter how to move. Every particle, planet, and photon would follow the shape of that curvature, like rivers flowing along the contours of a valley. To most physicists of the time, this sounded almost mystical. The notion that gravity could be geometry challenged every intuition built since Newton. Yet the logic was relentless, built from experiment and consistency. There was no other way to explain why acceleration and gravity were indistinguishable in every test. Einstein had glimpsed the hidden structure beneath the world's most familiar phenomenon. Gravity was not an invisible hand, but the shape of reality itself. The next step was to find the precise geometry that could describe this shape, and to reveal how matter and energy sculpt the stage on which all motion unfolds. If acceleration and gravity are identical, then perhaps both are merely the way we perceive curved space-time. Einstein's conviction that gravity and acceleration were the same kind of experience grew into a quest for mathematical expression. The world, he realized, could no longer be described with the rigid coordinates of Euclid. Flat geometry was insufficient to capture the flexibility that nature demanded. To express his idea, he turned toward a form of mathematics that had been developed half a century earlier, but was, at the time, considered little more than elegant abstraction: Riemannian geometry. Bernhard Riemann, a German mathematician of the 19th century, had shown that space could possess curvature, and that such curvature could vary from point to point. In Riemann's framework, the shortest distance between 2 points, a straight line in Euclidean space, could itself be a curved path if the space were distorted. This was not a philosophical idea, but a precise mathematical structure. It introduced the concept of a metric, a way to measure distance in any geometry, no matter how twisted or bent. Einstein saw immediately that this was the language he needed. He began to imagine the universe as a 4-dimensional continuum, composed of 3 spatial dimensions and 1 of time. This space-time could be curved by the presence of mass and energy. The motion of planets, light, and even time itself would then be governed not by forces, but by the geometry of this curvature. What we call gravitational attraction would simply be the motion of bodies following the straightest possible paths, geodesics, through curved space-time. Einstein's task was to connect this geometry with physics. He needed equations that could relate the curvature of space-time to the distribution of matter and energy. Working mostly alone in Berlin during the years leading up to 1915, he wrestled with this problem relentlessly. He corresponded with his mathematician friend Marcel Grossmann, who helped him navigate the complexities of tensor calculus, the mathematical language of Riemannian geometry. Step by step, Einstein built the foundation of what would become general relativity. His guiding principle was the equivalence of acceleration and gravity. Any observer in free fall should experience the laws of physics as if they were floating in deep space, unaffected by gravity. This required a theory that would preserve the same physical laws for all observers, regardless of their motion or position in a gravitational field. After years of struggle, the pieces finally fit together. In November of 1915, Einstein presented his field equations to the Prussian Academy of Sciences. The equations were compact but profound. On one side stood the geometry of space-time, expressed through a quantity known as the Einstein tensor, which described how curvature behaves. On the other side was the energy and momentum of matter, represented by another tensor. The two were connected by a constant that related the geometry of the universe to the strength of gravity. The essence of those equations could be expressed in a single poetic sentence. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. It was a self-consistent, self-sustaining relationship, a dance between geometry and existence. Gravity was no longer an external agent. It was the fabric of reality responding to what filled it. At first glance, these ideas seemed abstract, almost detached from the tangible world. But Einstein's theory was testable. It made predictions that differed sharply from Newton's. For example, light should not travel in a perfectly straight line near a massive object. Its path should bend slightly, curving along the warped geometry created by that mass. Likewise, the orbit of Mercury, whose precession had puzzled astronomers for decades, should be fully explained by the new equations. When Einstein performed the calculation, the result was exact. The precession of Mercury's orbit matched the observations perfectly. For the first time, a mystery that had resisted every attempt at explanation found its solution in the curvature of spacetime. This success convinced Einstein that he had found the right description of nature. But he knew that the true test would have to come from light itself. If gravity could curve the path of a beam of light, then the geometry of spacetime would reveal itself visibly in the sky. He predicted that during a solar eclipse, the light from distant stars passing near the edge of the sun would be bent, shifting their apparent positions slightly when compared with their normal locations in the night sky. This was an audacious claim. Newton's theory predicted a much smaller deflection, roughly half of what Einstein's equations required. A precise observation could decide, once and for all, which view of gravity was correct. But such an experiment was difficult. The light from stars near the sun could only be observed during the brief darkness of a total eclipse, when the moon blocked the sun's overwhelming glare. It would take 4 years, a world war, and a determined astronomer to provide that proof. In the meantime, Einstein refined his equations and shared them with a handful of trusted colleagues. Among them was Karl Schwarzschild, a German physicist serving on the front lines during the Great War. Even amid the noise of battle, Schwarzschild managed to find an exact solution to Einstein's equations for the gravitational field around a spherical mass. His result revealed something extraordinary: a region of spacetime so curved that light itself could not escape from it. Though Einstein did not grasp its full implications at the time, this would later become the mathematical description of a black hole. But for the moment, the focus was on the stars. The next total solar eclipse would occur in May of 1919. It would offer the first chance to test Einstein's bold prediction. Teams of astronomers prepared expeditions to 2 distant points on Earth: the island of Principe off the coast of Africa and Sobral in Brazil. Their mission was simple but monumental: photograph the stars near the sun's edge during the eclipse and measure whether their positions shifted by the precise amount Einstein's theory demanded. As the day approached, Einstein waited anxiously. He had built a universe where gravity was no longer a force, but geometry itself. If the starlight bent as he predicted, the illusion would be exposed. Not as deception, but as truth hidden in plain sight. Nature, for the first time, was about to reveal whether the shape of space could truly replace the pull of gravity. Equations alone were not enough. To prove gravity is geometric, nature had to bend light, shift time, and move stars accordingly. The day of the eclipse arrived on May 29, 1919. Across the Atlantic Ocean, 2 expeditions prepared for a moment that could redefine the laws of nature. One was led by Arthur Eddington, a British astronomer who had risked his reputation and resources to test Einstein's theory. He set up his equipment on the tiny island of Principe, where the eclipse would last just long enough to photograph the faint stars near the darkened edge of the sun. At the same time, another team positioned itself in Sobral, Brazil, to capture the same event from another part of the world, ensuring redundancy if clouds or mechanical failure interfered. The stakes were immense. If the starlight passing near the sun shifted by Einstein's predicted amount, roughly 1.75 arcseconds, then his theory would triumph. If the shift matched Newton's smaller estimate of 0.87 arcseconds, or if no shift was observed at all, Einstein's grand vision would collapse. The outcome would not only decide between two theories of gravity, but also determine whether the very fabric of space could bend under the weight of stars. As the eclipse began, the moon's shadow swept across the Earth, turning day into night for a few precious minutes. The astronomers worked in silence, photographing the stars whose light grazed the sun's surface. The conditions were difficult. In Principe, clouds threatened to ruin the observations. In Sobral, the heat distorted some of the images. But a handful of plates captured the necessary data. When the light returned, the teams packed their instruments and returned home to analyze the results. For months, Eddington and his colleagues compared the eclipse photographs to earlier reference images taken when the sun was nowhere near the same stars. The process required extraordinary care. Any tiny distortion of the photographic plates could mimic the effect they sought to measure. Yet, as the analysis continued, a clear pattern emerged. The stars near the sun's limb appeared displaced, not by Newton's expected value, but almost exactly by Einstein's prediction. When the results were announced in November 1919 at the Royal Society in London, the scientific world erupted. The data confirmed that light bends as it passes through the curved space-time near the sun. Gravity was not a force pulling on light, but the geometry of space guiding its path. Newspapers declared Einstein a new Newton, a revolutionary thinker who had remade the universe. His image, once that of an obscure physicist, became known around the globe overnight. But beyond the fame and the headlines lay something deeper. For the first time, humanity had experimental proof that space could curve. The old picture of a flat, mechanical universe was gone. The cosmos was flexible, dynamic, and alive with structure. Every star, planet, and galaxy shaped the space-time around it, and the curvature of that space-time determined the motion of everything within it. To Einstein, this confirmation was not just validation, it was relief. He had spent years doubting whether his abstract mathematics truly described the world. Now the evidence was written in the heavens. Light itself had traced the geometry of reality. Still, Einstein remained cautious. The eclipse results, while dramatic, were limited by the precision of early 20th century instruments. He knew that future tests would need to refine the measurements. Yet none of those later confirmations would change the essence of the discovery. Gravity was not a pull, but the shape of space and time. In the decades that followed, new observations continued to reinforce Einstein's theory. Radio signals passing near the sun experienced measurable delays. The orbits of binary pulsars revealed energy loss, consistent with gravitational waves, ripples in space-time that he had predicted in 1916. Each experiment added another layer of confidence, showing that the geometry Einstein described was real and universal. The success of the Eclipse expedition also carried a symbolic weight. It came just months after the end of the First World War, a time when Europe was fractured and weary. A British scientist had confirmed the theory of a German physicist, uniting minds across a world still recovering from conflict. Science, for a brief moment, transcended politics. The universe itself seemed to whisper a message of unity, that beneath division and distance, all things are connected through the same curvature of space-time. Einstein's equations had rewritten gravity, but they also reshaped humanity's understanding of its place in the cosmos. No longer was space a silent void or time a simple flow. Together, they formed a living fabric capable of bending and stretching under the influence of matter and energy. What Newton had seen as a pull between bodies was now seen as motion guided by geometry. The illusion of force had given way to a deeper truth. And yet, Einstein sensed that his journey was not complete. If space could curve, perhaps it could also ripple, carrying energy across the universe without any medium. In 1916, only a year after publishing his field equations, he proposed the existence of gravitational waves, disturbances in spacetime that travel outward from accelerating masses, like ripples spreading on the surface of water. For nearly a century, these waves would remain undetected, their existence doubted by many. But Einstein trusted the mathematics. If space could bend to guide light, then it could surely flex to carry waves. It would take the world another 100 years to confirm this final prediction, but the principle had already been set in motion. The bending of starlight had proven that space itself was not an illusion. It was the stage, the actor, and the story all at once. Gravity, once the most mysterious of forces, had been revealed as the shape of existence itself. Light had proven that space can curve. But if space can curve, can it ripple too? By the time the world grasped the meaning of Einstein's triumph, physics had entered a new era. The concept of gravity as a pull between objects was gone, replaced by something stranger and more elegant. The universe was no longer a rigid stage, but a living fabric. 4 dimensions interwoven into what Einstein called spacetime. It was the geometry of this fabric, not invisible forces, that determined how planets moved, how light traveled, and how time itself flowed. To appreciate how revolutionary this was, one must begin with Einstein's earlier work, Special Relativity. In 1905, Einstein had shown that space and time are not separate entities. They are fused into one continuum, and their measurements depend on how an observer moves. The faster one travels, the slower time passes, and the shorter distances become, all to preserve one unbreakable rule. The speed of light remains constant for all observers. This unification of space and time was the first hint that geometry, not mechanics, governs the structure of the universe. But special relativity applied only to uniform motion, where no acceleration or gravity was present. General relativity expanded the idea to include curvature, acceleration, and the influence of mass. In Einstein's vision, spacetime was not flat, but could bend, stretch, and twist. It was Riemannian geometry, mathematics that allowed space to be curved by the presence of energy and matter. To imagine curved spacetime, consider the surface of Earth. To someone walking across a small patch of ground, the world seems flat. But as one travels farther, the curvature becomes clear. Parallel lines eventually meet at the poles, and the sum of a triangle's angles exceeds 180 degrees. The same happens in the cosmos. On small scales, spacetime seems flat, but near massive bodies, it bends. The straightest path in such a curved geometry is not what we imagine as a straight line, but a geodesic, the shortest route between 2 points on a curved surface. For planets orbiting the Sun, these geodesics take the form of ellipses. The planets are not being pulled by an unseen force, but are freely following the curvature of spacetime caused by the Sun's mass. They are like marbles rolling across a stretched sheet that dips under a heavy sphere. To an observer standing nearby, the motion appears as circular or elliptical orbits. But in truth, each planet is simply moving straight through a curved geometry. The illusion of gravitational pull arises from our attempt to describe this motion in the language of flat space. Einstein's field equations made this concept precise. They described how the presence of mass and energy deforms space-time, and how that deformation, in turn, determines the motion of everything within it. The equations were not just elegant, they were self-consistent and universal. Whether describing the fall of an apple or the orbit of a galaxy, the same mathematical relationship held true. Karl Schwarzschild's solution, found in 1916, provided the first exact example. It described the geometry around a spherical mass such as a star or planet. From this solution emerged predictions that went far beyond Newton's framework. Time would slow down near strong gravitational fields. Light would bend. There existed a critical boundary, what later came to be called an event horizon, beyond which even light could not escape. Though Einstein himself doubted such extreme objects could exist in nature, Schwarzschild's results showed that spacetime's geometry could grow infinitely curved, forming what we now know as a black hole. The beauty of Einstein's equations lay in their simplicity and universality. They did not merely describe how matter moves, they described how space and time themselves behave. The geometry of spacetime is dynamic, responding to the distribution of energy and momentum everywhere. A star collapsing, a planet orbiting, or a beam of light traveling through the void. All of them are governed by the same relationship between energy and curvature. For the first time, gravity and geometry were one. The fabric of reality was no longer static, but active, alive with curvature that evolved with time. When a massive object moved or accelerated, it changed the geometry around it. In a sense, space was not an empty container, but a participant in the universe's evolution. To help others visualize this, physicists often use analogies, though none can fully capture the depth of four-dimensional curvature. One common image is that of a rubber sheet stretched tight. Place a heavy ball on it, and the sheet dips, curving the paths of smaller objects rolling nearby. The ball does not pull them directly, rather they follow the curved surface. But even this analogy is incomplete because it relies on gravity to make the sheet sag. In the true universe, space bends not because of an external pull, but because of the energy and mass within it. The curvature exists in space-time itself, without any higher dimension to hold it. Another way to think about curvature is through time rather than space. Imagine two people standing a short distance apart on Earth, both dropping identical balls at the same moment. The balls fall toward the planet's center along slightly converging paths because they are both following the geometry that leads inward. The convergence of those paths, the fact that the balls draw closer together, is a direct sign of space-time curvature. What we call the force of gravity is simply that curvature made visible. Einstein's insight also revealed why gravity has no direction or medium. In Newton's picture, gravity acted instantaneously across space. In Einstein's, changes in the curvature of space-time propagate at the speed of light, ensuring causality and consistency. If the Sun were to vanish suddenly, Earth would continue orbiting its last known curvature for about 8 minutes, the time it takes light, and therefore any change in geometry, to reach us. The universe communicates through geometry, not through invisible forces. This framework also transformed the understanding of energy. In Einstein's universe, energy and mass are equivalent, a relationship captured by his earlier equation: energy equals mass times the speed of light squared. The energy contained in light, radiation, or motion all contributes to the curvature of space-time. A beam of light, though massless, can bend the path of another beam. The geometry of the cosmos responds not just to substance, but to every form of energy that moves within it. The general theory of relativity was more than a set of equations. It was a new way to see reality. It replaced the mechanical certainty of Newton's world with a dynamic continuum where geometry and matter co-created one another. Every movement of mass reshaped space, every passage of time unfolded along that new geometry. At its core, Einstein's vision carried a subtle but profound message. What we perceive as forces may often be illusions born from perspective. The apple does not fall because it is pulled. It falls because its path through curved space-time leads downward. The planets do not swing around the sun because they are bound by attraction. They glide effortlessly along the contours of a cosmic geometry sculpted by mass and time. Einstein's universe was not empty. It was structure itself, woven with curvature that governed the rhythm of everything from falling leaves to the light of distant galaxies. Yet as elegant as this geometry was, it could not rest untested. Equations alone, no matter how beautiful, mean nothing without nature's confirmation. The true test would come not from blackboards, but from the sky. If space could curve, then light must follow that curve. If time could stretch, then clocks must slow down in gravitational fields. The bending of light and the warping of time were no longer philosophical possibilities. They were predictions waiting for proof. Equations alone are not enough. To prove gravity is geometric, nature must bend light, shift time, and move stars accordingly. Einstein's field equations had rewritten the laws of gravity, but proving them would require the cooperation of the universe itself. The first opportunity had come and gone with the 1919 eclipse, which showed that starlight bends around the sun exactly as predicted. Yet that was only the beginning. The deeper test lay not just in bending light, but in how this geometry affected time itself. If gravity was curvature, then clocks would not tick the same everywhere. Einstein understood that time and space were inseparable. In his universe, when space-time curves, time stretches or compresses just as space bends. Near a massive body, where curvature is strong, time slows down. Far from mass, where space-time is nearly flat, it runs faster. This prediction was radical, but it emerged naturally from his equations. To test it would mean measuring differences in time between places of different gravitational potential, something no one had yet done. The first hints came from the motion of Mercury, already explained perfectly by Einstein's theory. But to verify the warping of time itself would take new technology and new precision. In 1959, the Rebka experiment at Harvard University used gamma rays to measure gravitational redshift, the way light loses energy climbing out of Earth's gravitational field. The result matched Einstein's prediction exactly. Time on the ground, deeper in Earth's gravity, runs infinitesimally slower than time at the top of a tower. This was more than a curiosity. It meant that every clock in the universe, from the most advanced atomic instrument to the ticking of a human heart, was influenced by curvature. The flow of time was not universal, but relative to position in the gravitational field. Einstein's equations predicted even more astonishing effects. If space could curve, it could also ripple. Accelerating masses, like orbiting stars, should send waves of distortion through space-time itself. These gravitational waves would be unimaginably faint, stretching and compressing space by less than the width of an atom over kilometers of distance. For decades, scientists debated whether such waves could ever be detected. Einstein himself doubted they would be observed, believing them too weak to measure. But the universe is patient. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a pair of neutron stars orbiting one another, a binary pulsar system radiating energy away in just the manner Einstein's equations predicted. Their orbital period was shrinking exactly as it should if gravitational waves were carrying energy outward. This was indirect evidence, but it was powerful enough to earn them the Nobel Prize 2 decades later. Still, direct detection remained elusive. To observe space-time itself vibrating required instruments of unprecedented sensitivity. Scientists around the world began building vast interferometers, capable of measuring changes smaller than a fraction of a proton's width. After decades of effort, in September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the faint tremor of space-time from the collision of 2 black holes more than 1 billion light-years away. The signal was brief but unmistakable, a rising chirp that matched the exact waveform predicted by general relativity. 2 massive black holes had spiraled together, merging into one and sending ripples through the fabric of space-time that reached Earth after traveling for over 1 billion years. It was as if the universe itself had spoken in the language of Einstein's equations. The detection confirmed what Einstein had imagined a century earlier. Gravity was not the mysterious pull acting through empty space, but the shape of space-time itself. When masses move, they disturb that geometry, and those disturbances travel as waves. The cosmos, in its silence, carries music in its curvature. What made the discovery so remarkable was not only its precision, but its implication. Gravity required no medium, no ether, and no invisible cords connecting masses. It propagated through the structure of space-time itself. The ripples detected by LIGO were not vibrations in some unseen field. They were vibrations of reality's geometry. This understanding deepened humanity's sense of connection to the cosmos. Every star that collapses, every galaxy that collides, every cataclysmic event anywhere in the universe sends ripples through space-time, faint echoes that can be heard with the right instruments. The universe is not static but dynamic, filled with the slow breathing of curved geometry, stretching and relaxing as it evolves. Einstein's theory had survived every test, from the bending of starlight to the slowing of clocks, from the orbit of Mercury to the ripples of gravitational waves. Every observation confirmed that gravity was not a force, but the manifestation of curved space-time. Yet for Einstein, this realization was never a dismissal of Newton, but a continuation. Newton's laws remained accurate in regions where curvature was mild, just as Euclid's geometry works perfectly on a small patch of Earth. But when space bends sharply, near stars, black holes, or across cosmic distances, only Einstein's geometry reveals the truth. The success of general relativity transformed not just physics, but philosophy. It redefined what it means for something to exist. Space and time were no longer the backdrop against which matter moves. They were entities in their own right, capable of interacting with energy and shaping the universe's destiny. Einstein once remarked that the most incomprehensible thing about the universe is that it is comprehensible. His equations turned that mystery into clarity. The cosmos, vast and complex, obeys a geometry that human minds can grasp. What we feel as gravity is the simplest experience of that geometry. When we drop a stone, it follows the natural curve of space-time. When we orbit a star, we are tracing the contours of a cosmic valley. The pull we feel is not a tug from afar, but a shadow of the curvature beneath our feet. Einstein's illusion had become the foundation of modern physics. Gravity was no longer the most mysterious of forces. It was a property of the universe itself, woven into the structure of reality. Einstein's illusion deepened, because what we once called gravity is not a pull, but the geometry of motion in a dynamic fabric. In the spring of 1919, as the world emerged from the devastation of war, a quiet scientific drama was unfolding that would change humanity's perception of reality. For centuries, gravity had been seen as a mysterious attraction between masses. Now, a new idea was being tested, that this attraction was not a force at all, but the manifestation of curved spacetime. To prove it, nature would have to show that light itself, the most incorporeal thing known, could be bent by the presence of mass. Einstein's equations predicted that light passing near a massive body should follow a curved path. The curvature of spacetime near the Sun would deflect the light of background stars by about 1 3/4 arc-seconds, roughly twice what Newton's theory predicted. It was a minute difference, but in it lay the potential to overthrow 2 centuries of classical physics. Arthur Eddington, an English astronomer and director of the Cambridge Observatory, understood the magnitude of what was at stake. Despite lingering post-war tensions between Britain and Germany, Eddington recognized Einstein's theory as one of the most beautiful ideas ever proposed. He also saw that the upcoming total solar eclipse on May 29, 1919, would provide a perfect opportunity to test it. During an eclipse, the blinding glare of the Sun is blocked by the Moon, allowing stars near the solar disk to become visible for a few minutes. If their apparent positions shifted outward, it would mean that space-time itself was curved. Eddington organized 2 expeditions. One team would travel to the island of Príncipe, off the coast of Africa, while another would set up instruments in Sobral, Brazil. It was a colossal effort in an age when travel was uncertain and equipment delicate. Large telescopes and photographic plates had to be transported across oceans and through tropical climates. Everything depended on weather, precision, and a few fleeting minutes of darkness. When the day came, clouds threatened to obscure the view in Príncipe. Eddington waited in tense silence as the Moon began to slide across the Sun. For 6 minutes, daylight faded to a ghostly twilight. The corona flared into view, and against it, a few faint stars appeared. Through the gaps in the clouds, Eddington's team managed to capture several photographs before the light returned. At Sobral, conditions were clearer, and the second team obtained more images, though heat and mechanical distortions complicated the measurements. Back in England, months of meticulous analysis followed. Eddington compared the positions of stars photographed during the eclipse to reference images taken when the Sun was far away from that region of sky. The task required painstaking attention. Even the tiniest distortion of the photographic plates could create false readings. Yet, after countless measurements, one result stood out. The starlight had indeed shifted, not by Newton's expected half value, but by the full amount predicted by Einstein's equations. When the findings were presented to the Royal Society in London on November 6, 1919, the announcement electrified the world. The Times of London declared, "Revolution in science, new theory of the universe, Newtonian ideas overthrown." The New York Times followed with the now famous headline, "Lights all askew in the heavens." In an instant, Einstein became a global icon, his name synonymous with genius. But beyond the headlines, a deeper truth had emerged. Space was not a passive void. It could bend, and in that bending lay the true nature of gravity. To many, the idea that light, the ultimate symbol of straightness, could curve seemed impossible. But Einstein's theory explained it perfectly. Light always travels along the straightest possible path in space-time. When space-time itself is curved, that path appears bent to us. The deflection of starlight by the Sun was not a distortion of light's behavior, but a revelation of the geometry it followed. The eclipse experiment also unified 2 fundamental concepts. It proved that energy, even without mass, responds to gravity. Light, despite being massless, carries energy and momentum, which means it must follow the curvature of space-time like any other entity. This insight extended Einstein's principle of equivalence to its logical extreme. Gravity affects everything, even light itself. Skeptics demanded more proof. The 1919 Eclipse data, while compelling, was gathered under difficult conditions, and the precision of instruments left room for doubt. But as the decades passed, newer observations confirmed the result with ever-increasing accuracy. Radio signals from distant quasars, gravitational lensing of galaxies, and spacecraft experiments all demonstrated the same thing. Space-time bends exactly as Einstein predicted. One of the most striking confirmations came from the discovery of gravitational lenses. Cosmic magnifying effects, where massive galaxies or clusters bend the light of more distant objects, producing multiple images or arcs in the sky. These lenses, first observed in the late 20th century, are among the most beautiful manifestations of general relativity. They allow astronomers to see galaxies billions of light years farther than would otherwise be possible. Eddington's success marked a turning point not just for physics, but for the philosophy of science itself. For the first time, a purely theoretical idea, born from equations and thought experiments, had been verified on a cosmic scale. It showed that human reason could reach beyond direct experience to describe the fabric of the universe itself. Einstein, upon hearing the confirmation, was calm. When a colleague asked what he would have done if the experiment had disproved his theory, he famously replied, "Then I would have been sorry for the dear Lord, for the theory is correct." It was not arrogance, but confidence born from years of relentless logic. The geometry of space-time was no longer speculation. It had become observation. The success of the Eclipse expedition also carried a quiet symbolism. At a time when nations were still recovering from conflict, a British scientist had validated the theory of a German physicist. Science had transcended borders, uniting minds in pursuit of truth. The universe, impartial and vast, had provided the stage for reconciliation through understanding. From that day forward, the Newtonian picture of gravity would remain a useful approximation, but no longer the ultimate truth. Every planet, every photon, every clock ticked within Einstein's curved cosmos. The path of light had revealed that space itself was an active participant in the universe's story. But Einstein's journey did not stop there. If space could curve, he reasoned, it could also ripple. Just as a stone dropped into a pond sends waves across its surface, massive objects accelerating through space-time should generate ripples, gravitational waves, carrying energy outward. It would take nearly a century for humanity to detect those ripples. But the idea was already present in Einstein's mind as he basked in the quiet aftermath of the eclipse. The illusion of gravity as a force had been shattered, replaced by a living, dynamic geometry that could bend, twist, and move. Light had proven that space can curve. But if space can curve, can it ripple too? Einstein published his prediction of gravitational waves in 1916, only months after finalizing his field equations. He had realized that if spacetime could curve, then any acceleration of mass should send ripples through that curvature, distortions that travel outward at the speed of light. These ripples would not move through a medium like air or water. They would be oscillations of spacetime itself, faint but real, carrying energy across the universe. At first, even Einstein doubted whether such waves could ever be detected. The distortions they produced would be unimaginably small. A passing gravitational wave might stretch and compress a distance of 1 kilometer by less than a fraction of a proton's width. Yet he was certain they must exist. The universe could not flex without creating motion, and that motion had to travel. For decades, the idea remained theoretical. Astronomers and physicists debated whether the waves were genuine physical entities or mathematical artifacts of Einstein's equations. Some believed they would cancel out, leaving no measurable effect. Others suspected that even if they existed, humanity would never possess the instruments sensitive enough to detect them. The argument continued through much of the 20th century, quietly waiting for technology to catch up with theory. Evidence began to appear indirectly. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars locked in a tight orbit, whirling around each other with astonishing precision. By measuring the timing of the pulses, they found that the orbit was slowly shrinking, losing energy exactly as Einstein's equations predicted. The missing energy, they concluded, was being carried away by gravitational waves. It was the first confirmation that the waves were real, though no one had yet seen them directly. It took another 40 years for the final proof to arrive. The Laser Interferometer. Gravitational Wave Observatory, LIGO, was built with one purpose: to detect the stretching and squeezing of space-time itself. Each LIGO detector consisted of two long arms arranged in an L shape, each several kilometers in length. Laser beams bounced back and forth along these arms, and any passing gravitational wave would change the relative lengths ever so slightly, producing an interference pattern. For years, the detectors remained silent. Engineers refined the instruments, reducing noise and vibration to levels never achieved before. Then, on September 14, 2015, a faint signal arrived, a gentle, rising chirp that lasted less than a second. It matched exactly the pattern predicted for two black holes spiraling together and merging more than 1 billion light-years away. This single observation marked one of the greatest triumphs in the history of science. Humanity had detected the motion of space-time itself. Einstein's waves, once dismissed as impossible to observe, had crossed 1 billion years of cosmic distance to reach a small planet orbiting an ordinary star. The details of the detection were breathtaking. The two black holes had masses of about 30 and 35 times that of the Sun. As they merged, they converted a portion of their mass into energy, radiating it as gravitational waves in a fraction of a second. The power released was greater than that of all the stars in the observable universe combined, yet the effect at Earth was so slight that it changed LIGO's arms by less than 1/10,000th the diameter of a proton. The success of LIGO confirmed not only Einstein's theory, but the profound unity of nature. Space and time were not passive backgrounds, but dynamic entities capable of motion. The universe could ripple, breathe, and carry energy without any medium. Reality itself was elastic. In the years since that first detection, dozens of additional gravitational wave events have been recorded. Black hole mergers, neutron-star collisions, and possibly even the echoes of the universe's earliest moments. Each signal adds another chapter to the story Einstein began a century earlier, turning abstract geometry into a cosmic symphony. The discovery also linked general relativity with other realms of science. Astrophysicists could now study violent events otherwise hidden from view. Gravitational waves pass through matter unhindered, revealing the invisible interiors of stars and the structure of space-time near black holes. Cosmologists hope to detect the faint background hum left over from the Big Bang itself, a fossil record of the universe's birth written not in light, but in geometry. Einstein would have been astonished by the sensitivity and precision of the instruments that proved his vision. When asked about gravitational waves during his lifetime, he had alternated between confidence and doubt. Yet the mathematics had always guided him. It told him that the universe was not static, but alive with motion, and that every acceleration of mass sent tremors through the fabric of reality. The detection of those tremors completed one of the most remarkable journeys in science. From Newton's invisible force to Einstein's curved space-time, from untested equations to the direct observation of ripples in the geometry of the cosmos. Gravity, once the most mysterious of interactions, had been stripped of its mystique and revealed as the architecture of existence itself. After LIGO's announcement, physicists around the world paused to reflect on what had just occurred. The discovery did not merely confirm a theory, it proved that the universe communicates through curvature. Every star that explodes, every galaxy that collides, every black hole that merges sends messages across space and time, and humanity had finally learned to listen. The illusion Einstein uncovered was now complete. What had once been imagined as an invisible pull turned out to be the restless geometry of space-time in motion. The universe is not silent. It hums, it ripples, and it speaks through the fabric of reality itself. Einstein's illusion deepened. What we once called gravity was not a force, but the dance of geometry and motion, written in the vibrations of space-time. The news of LIGO's discovery spread across the world like a second sunrise. For the first time in history, humanity had not just seen the universe, it had heard it. The faint signal that reached Earth in 2015 was a vibration of space-time itself, a whisper from two black holes that had collided more than 1 billion years ago. The sound, converted into audio frequencies, rose in pitch as the black holes spiraled together, ending with a brief, sharp chirp. It lasted less than half a second, but in that moment, the fabric of reality spoke with the voice of Einstein's mathematics. What the world celebrated as a technological triumph was, in truth, the confirmation of an idea so subtle and profound that even Einstein had once doubted its measurability. The waves had carried no material, no energy through a medium. They were pure curvature traveling through the structure of space-time itself. They did not move in space, they were the motion of space. Every crest and trough represented the stretching and squeezing of reality in alternating directions, as though the universe itself were breathing. Physicists listened to the data in awe. The black holes that produced the signal had orbited one another for millions of years, drawing ever closer as they radiated energy through gravitational waves. In their final moments, they circled hundreds of times per second before merging into one. The collision released energy equivalent to 3 times the mass of the Sun in less than a heartbeat, all converted into ripples that spread outward at the speed of light. By the time those ripples reached Earth, their power had faded almost to nothing, but their form remained perfect. Each new detection since then has been a chapter in the same story. Binary black holes colliding, neutron stars merging, and perhaps even future echoes from the dawn of time itself. Gravitational waves have given scientists a new sense, one that does not rely on light. With this sense, they can observe the dark side of the cosmos, regions where light cannot escape, yet where the geometry of space-time still reveals the events within. It is a window not just into matter, but into the behavior of the universe's very fabric. The confirmation of gravitational waves also linked Einstein's vision with the cosmic scale of modern astronomy. When 2 neutron stars collided in 2017, LIGO and its European counterpart, Virgo, detected their gravitational waves, while telescopes around the world caught the burst of light that followed. For the first time, humanity saw and heard the same cosmic event. The waves and the photons told the same story, arriving together from 130 million light-years away. Einstein's geometry had become an instrument of cosmic harmony. Each of these discoveries reaffirmed a truth that had first emerged from the Eclipse of 1919. The universe is not a stage, but a structure in motion. Every star, planet, and atom is woven into the same fabric, contributing its own subtle vibration to the cosmic whole. Even empty space is not truly empty. It can curve, stretch, and carry energy, shaping the evolution of galaxies and the flow of time. The elegance of this realization lies in its simplicity. What we experience as weight or pull is only our resistance to free fall. What we call the attraction of gravity is nothing more than geometry guiding motion. And when that geometry changes, when masses accelerate or collide, the universe itself ripples, broadcasting the story of its motion across billions of light years. Yet Einstein's discovery of gravitational waves was not only a scientific victory, it was a philosophical one. It demonstrated that reality is not static, but dynamic, a living continuum that responds to every change within it. The universe is not a collection of things moving through emptiness. It is the interplay between energy, time, and curvature. In that sense, gravity was never a separate phenomenon at all. It was the shape of existence itself. Looking back, the journey from Newton to Einstein seems inevitable, yet it required a leap of imagination, as great as any in human history. Newton's force explained motion but left action at a distance as a mystery. Einstein replaced that mystery with geometry. And now, through the detection of gravitational waves, the final veil was lifted. The geometry itself could move, carrying messages across the cosmos. This was the moment when the illusion of gravity became fully visible. There was no unseen hand pulling the planets in their orbits, no force transmitted through the void. There was only space-time, curved and alive, guiding motion according to its shape. What we call gravity is the experience of living inside that geometry. The detection of gravitational waves also hinted at questions yet to be answered. If space-time can ripple, what happens where it curves infinitely? At the heart of a black hole? If geometry itself can move, can it also break down? Could the earliest moments of the universe have been a storm of chaotic space-time waves still echoing faintly across the cosmos? These mysteries pointed forward, toward the next great frontier of physics. For Einstein, the dream had been fulfilled. Geometry had replaced force, curvature had replaced attraction, and motion itself had become the language of the universe. But nature still had one more revelation to offer, one that would stretch his ideas to their most extreme, the places where curvature becomes infinite and space-time collapses upon itself. Light had proven that space can curve, and the waves of space-time had shown that it can ripple. Now the universe would reveal what happens when curvature becomes absolute. Einstein's illusion deepens, because what we once called gravity is not a pull, but the geometry of motion in a dynamic fabric. Einstein's triumph over Newton's force of gravity did not end with the bending of starlight or the detection of ripples in space-time. His equations contained something far more profound, a realization that space and time are not passive arenas through which matter moves, but active, evolving entities. Space itself can move. It can expand, contract, and twist. What we perceive as motion through space is, in truth, motion with space. When Einstein first formulated his general theory of relativity in 1915, he believed the universe must be static. At that time, scientists assumed the cosmos was eternal and unchanging on the largest scales. But his equations refused to cooperate. When he applied them to the entire universe, they predicted instability. The cosmos should either expand or collapse under its own gravity. To restore balance, Einstein introduced a term he called the cosmological constant, a mathematical adjustment that counteracted gravity and held the universe in equilibrium. It was a compromise meant to preserve harmony between theory and the assumptions of his age. That illusion was shattered a decade later. In 1929, Edwin Hubble, observing distant galaxies from Mount Wilson Observatory, discovered that the light from those galaxies was redshifted, stretch toward longer wavelengths. The farther away a galaxy was, the greater its redshift. Hubble's observations revealed that the universe was expanding, not static. Space itself was stretching, carrying galaxies apart like dots on the surface of an inflating balloon. Einstein's response was immediate and humble. He called his introduction of the cosmological constant his greatest blunder, though modern cosmology would later resurrect that same term to describe the mysterious force of dark energy. The important realization was that expansion was not motion through space, but motion of space. The galaxies were not flying apart into empty nothingness. Rather, the very fabric of space-time between them was growing. This was perhaps the most radical consequence of Einstein's equations. They described a universe where geometry evolves with time, where the separation between galaxies increases not because they travel through a fixed void, but because the void itself changes in scale. It meant that the universe had a history, a beginning, and perhaps an end. The cosmos was dynamic, alive with motion that no external force commanded. Space could now be seen as a participant in cosmic events. When a star collapses under its own gravity, it does not fall into a pre-existing void. It drags the fabric of space-time inward with it, twisting and compressing the geometry itself. When two black holes spiral together, the space around them churns like a sea, sending gravitational waves outward. These are not disturbances moving through space, but movements of space. Einstein's realization connected the grandest cosmic motions with the simplest experience of falling. An object in free fall is not being pulled downward, it is simply following the natural flow of space-time. When you drop a stone, the curvature of space-time guides its motion. When a galaxy drifts away from another, it is carried by the expansion of space-time. Gravity, motion, and the structure of the universe are all expressions of the same geometry in motion. This geometric view explained phenomena that once seemed impossible. The slowing of time near massive bodies, the orbit of planets, and the expansion of the universe all arose naturally from the same set of equations. Matter tells space-time how to curve, space-time tells matter how to move, and that interplay shapes everything from falling apples to cosmic acceleration. Over the decades, new discoveries continued to confirm this vision. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, revealed that the universe had once been denser, hotter, and smaller. This confirmed that space-time itself had expanded from an initial singularity roughly 13.8 billion years ago. The expansion was not like an explosion into emptiness, but a stretching of geometry itself, carrying all matter and energy within it. At small scales, the curvature of space-time determines the motion of planets and light. At the largest scales, it determines the destiny of the cosmos. Whether the universe will expand forever, slow to a stop, or collapse, depends on the total balance between the energy of matter and the curvature of space. For the first time in history, geometry was no longer abstract. It was the story of everything that moves, from atoms to galaxies. In Einstein's view, the geometry of space-time was an illusion only in the sense that what we experience as force or attraction is not fundamental. The apple falls because the geometry beneath it changes as it moves, guiding it naturally along a curve that leads to Earth's surface. Astronauts orbit Earth not because they are held by a tether of invisible force, but because they are following a circular geodesic in curved space-time, a path that continuously falls around the planet. Even their weightlessness is not a lack of gravity, but a perfect surrender to geometry. The first people to experience this directly were astronauts aboard early space missions. When they entered orbit, they felt the sensation of floating freely, as if gravity had vanished. But in truth, they were not beyond its reach. They were in perpetual free fall, moving so fast that Earth's curvature kept receding beneath them. Their apparent weightlessness was the most direct experience of Einstein's vision, life inside a geometry where force has dissolved into motion. This understanding transformed not only physics, but engineering. The trajectories of spacecraft, the orbits of satellites, and even the operation of global positioning systems depend on general relativity. Without accounting for the curvature of space-time, satellites would drift and GPS signals would accumulate kilometers of error each day. Einstein's equations, born from pure thought, became the invisible structure of modern civilization. Yet for all its power, Einstein's theory also contained a profound humility. It suggested that even the grandest movements of the universe are not driven by external cause, but are expressions of the geometry within. There is no invisible hand, no separate force commanding matter. There is only curvature, evolving according to the balance of energy and time. The realization that space itself can move forced physicists to reconsider what the word motion even means. If all things move within space-time, and space-time itself moves, what is left to define stillness? In Einstein's cosmos, there is no absolute rest. Everything is part of an ever-changing continuum. Even the void between galaxies participates in the dance, stretching and shifting as the universe grows. The illusion of gravity as a pull had been completely undone. What remained was more astonishing: a universe that moves itself. Space-time is not the emptiness between things. It is the thing itself. The invisible ocean whose tides carry stars and galaxies, whose waves ripple from cosmic collisions, and whose expansion defines the passage of cosmic history. Einstein's insight had turned Newton's mystery of attraction into geometry, and then transformed geometry into motion. Gravity was not a thing acting upon the universe, it was the universe acting upon itself. Einstein's illusion deepens, because what we once called gravity is not a pull, but the geometry of motion in a dynamic fabric. Einstein's realization that space itself could move reshaped not only the science of the cosmos, but also the way humanity understood motion, energy, and even existence. In his framework, there was no longer a clear boundary between what moves and what is moved. The universe had become a single, interwoven fabric in which matter and geometry continuously shaped each other. The equations of general relativity described this dance with mathematical precision, but their implications extended far beyond mathematics. They revealed a universe that was alive, dynamic, self-evolving, and profoundly interconnected. For most people, the idea that space itself moves is difficult to grasp. We imagine galaxies flying apart through emptiness, like sparks from a fire. But Einstein's equations show that the galaxies themselves are not propelling outward through pre-existing space. Instead, it is the fabric of space-time that is stretching, and the galaxies are merely carried along with it. Every meter between them expands with time, while locally, in our solar system or within a galaxy, the geometry remains tightly curved and stable. This is why we do not feel the expansion. We move with it. To visualize this, cosmologists often use the analogy of a balloon covered with small dots. As the balloon inflates, the dots move away from each other, though none of them travel across the surface. The surface itself expands, carrying the dots apart. That surface represents space-time, and its stretching represents the expansion of the universe. There is no center, no edge, no boundary expanding into anything else. The universe expands not into space, but within itself. The motion of space also means that the distance between distant galaxies can increase faster than the speed of light. Not because any object moves faster than light through space, but because the space between them expands. This subtlety, often misunderstood, preserves the cosmic speed limit while allowing the universe to grow beyond the limits of any individual signal. The geometry of space-time does not merely host motion, it defines it. Einstein's vision predicted that such curvature and expansion would affect the behavior of time as well. In an expanding universe, clocks run differently depending on where and how they move. A clock aboard a satellite orbiting Earth ticks faster than one on the ground because it experiences weaker gravity, while a clock deep within a massive object would tick more slowly. These effects, tiny yet measurable, are not corrections to time, but reflections of what time is, a dimension intertwined with space, bending and stretching with geometry. This principle is what allows global positioning systems to function. The satellites that orbit Earth must account for both special and general relativity. Their onboard clocks, high above Earth's surface, experience less gravitational curvature and therefore tick slightly faster. Without Einstein's equations, GPS devices would drift by several kilometers each day. The same geometry that guides the motion of planets and bends starlight also guides every moment of human navigation. On cosmic scales, the moving geometry of space-time tells a still larger story. The expansion that Hubble observed in 1929 has never stopped. Measurements of the cosmic microwave background, the faint afterglow of the early universe, show that the cosmos has been expanding for roughly 13.8 billion years. Yet recent observations reveal that the expansion is not slowing down under gravity's pull as once expected, but accelerating. Something, an unknown energy inherent to space itself, is driving this acceleration. Physicists now call it dark energy, and it is one of the deepest mysteries of modern science. It behaves as if every region of space contains a small, constant amount of energy that does not dilute as the universe expands. The more space there is, the more dark energy exists, pushing the expansion ever faster. In Einstein's equations, this phenomenon can be represented by the same cosmological constant he once dismissed as a mistake. What he called his greatest blunder may, in the end, describe the fate of the cosmos. The idea that space can move, stretch, and even accelerate on its own dissolves the distinction between geometry and physics. It shows that the fabric of reality is dynamic and creative. When a star dies and collapses, it warps the geometry around it, forming a black hole. When two black holes merge, they send gravitational waves through space-time. When the universe expands, it carries galaxies apart like leaves on a rising tide. In every case, motion and structure are the same thing viewed from different perspectives. This unity extends even to the smallest scales. In the realm of quantum physics, where particles and waves coexist in strange superpositions, space-time is no longer smooth, but froths with uncertainty. The general relativity that so beautifully describes planets and galaxies begins to falter here. At the Planck scale, far smaller than any atom, the geometry of space-time might fluctuate wildly, defying classical understanding. Physicists believe that in those tiny regions, the distinction between matter and geometry could blur completely. The fabric of space-time itself might emerge from more fundamental principles still unknown. Einstein, however, remained cautious. He saw the completeness of general relativity not as final truth, but as a stage along the path toward deeper understanding. He once said that theories should be as simple as possible, but not simpler. His equations were simple, a handful of symbols that captured the structure of the cosmos, yet they hinted at layers beneath them, places where geometry and quantum mechanics would one day meet. The realization that space can move also changes how we perceive our place in the universe. Everything that exists, from galaxies to atoms, participates in this expansion. Even as we stand still, the space around us is part of a cosmic current that has been flowing since the dawn of time. To live in this universe is to float within a vast ocean whose tides are invisible, but whose influence touches everything. Einstein's illusion, then, was not that gravity itself is false, but that its nature is misunderstood. What we call gravity is the appearance of motion within curved and expanding space-time. What we experience as falling, orbiting, or floating is simply our participation in the geometry that defines reality. The motion of space itself is the universe's most elegant deception, an illusion that hides the truth that nothing is separate, that every particle, every beam of light, and every instant of time are bound together in the same continuum. It is not emptiness that fills the cosmos, but the geometry of existence itself, always moving, always evolving, always alive. Einstein's illusion deepens. What we once called gravity is not a force, but the movement of the very stage on which reality unfolds. Einstein had transformed humanity's understanding of motion and force, yet even he could not have predicted how his ideas would ripple through time. His theory revealed that space and time were not fixed backgrounds, but participants in the unfolding of the universe. The motion of space itself was now a central truth of physics. And while the expansion of the cosmos played out across billions of light years, the same principles guided the fall of a stone, the orbit of the moon, and the arc of a spacecraft navigating the void. To grasp this, imagine the Earth circling the Sun. In Newton's world, the planet is bound by a gravitational force pulling it inward. In Einstein's world, the Earth is free. It moves along the straightest possible path, a geodesic, through curved space-time. The Sun's mass bends space-time around it, creating the valley through which Earth travels. The planet is not being pulled by any invisible thread. It is falling endlessly, tracing the natural curve of the universe's geometry. Now imagine that same motion scaled up to cosmic proportions. Galaxies drift apart, not because they are flung outward by an explosion, but because the space between them is stretching. The same geometry that curves around stars and black holes also expands between galaxy clusters. The entire universe is a flowing landscape, with curvature shaping the motion of everything inside it. The laws that describe this motion are the same at every scale. The concept that space itself moves also reshaped the way physicists understand energy. In classical mechanics, energy was something contained within objects, the motion of particles, the pull of forces. In relativity, energy and mass became interchangeable, and both were woven into the fabric of space-time. The geometry of the universe was not just shaped by matter, but by energy in all its forms: light, heat, motion, and even vacuum energy. The curvature of space is the manifestation of the total energy contained within it. This meant that even the most familiar experiences, standing, falling, resting, are interactions with geometry. When you stand still on Earth, you are not in equilibrium. You are resisting free fall. The ground pushes upward, preventing you from following your natural geodesic through curved space-time. The sensation of weight you feel is not the pull of gravity, but the resistance to motion through geometry. Astronauts in orbit experience the opposite. They are constantly falling, but because their motion curves perfectly around Earth, they never collide with it. Their weightlessness is not an absence of gravity, but the perfection of free fall within spacetime's curve. This insight carries extraordinary consequences. It means that motion through spacetime defines everything we experience as force. What feels like attraction or pressure is simply geometry asserting itself. The more massive the body, the more it curves spacetime, and the stronger the deviation of nearby geodesics. Gravity, then, is not a universal force acting at a distance, but the local effect of the geometry created by mass and energy. The universe does not push or pull. It bends. This bending shapes not only the trajectories of objects, but also the passage of time. Clocks run slower near massive bodies because the curvature of space-time makes time itself flow differently there. A clock on Earth ticks more slowly than one aboard a satellite in orbit. The difference is small, only microseconds per day, but measurable. Without adjusting for that effect, satellite navigation systems like GPS would fail almost immediately. Every moment of synchronization across the planet depends on Einstein's realization that time itself is elastic. The motion of space also explains the structure of the universe on its largest scales. When cosmologists simulate the evolution of galaxies, they do not imagine them moving through static emptiness. They calculate how space-time itself stretches, how curvature evolves as matter clusters under its own geometry, and how expansion changes the distance between those clusters over billions of years. The cosmic web of galaxies that telescopes reveal, a vast network of filaments and voids, is not only a map of matter, but a map of space-time in motion. As the universe expands, distant galaxies recede faster and faster, and their light shifts toward redder wavelengths. The further they are, the greater the red shift, not because they are speeding through space, but because space itself stretches the light's wavelength as it travels. This phenomenon, first observed by Edwin Hubble, remains one of the most direct pieces of evidence for Einstein's dynamic cosmos. The discovery of cosmic expansion raised a question that still puzzles scientists today. If space is expanding, what drives it? For decades, physicists assumed that the expansion would slow over time, gradually halted by the pull of matter's curvature. But in 1998, observations of distant supernovae revealed something astonishing. The expansion was accelerating. The universe was not being slowed by gravity, it was being pushed by something unseen. This mysterious influence, now called dark energy, behaves like a property of space itself, a uniform energy that remains constant as the universe grows. It does not dilute as galaxies move apart. Instead, it drives them faster away from each other. The equations of general relativity can describe this behavior through Einstein's cosmological constant, the very term he once thought a mistake. It seems that his greatest blunder may have been an unintentional prediction of the universe's accelerating fate. If this continues indefinitely, the galaxies now visible to us will eventually drift beyond the cosmic horizon, their light stretched into invisibility. The universe will grow cold and dark, not because matter disappears, but because the geometry of space carries everything apart faster than light can bridge the gaps. The cosmos will fade not into emptiness, but into infinite separation. The motion of space itself creating a stillness beyond perception. Einstein's revelation that space could move transformed gravity from a pull into a story of unfolding geometry. What began with the fall of an apple had expanded into the motion of galaxies and the birth of the cosmos itself. The same equations that described an orbiting planet also describe the stretching of space-time across billions of light years. In this vision, there are no forces reaching across the void, no invisible lines of attraction binding distant worlds. There is only geometry, moving and reshaping, guiding everything along its contours. What we once called gravity is simply the universe in motion, a geometry that curves, stretches, and breathes, carrying us within it. Einstein's illusion deepens, because what we once called gravity is not a pull, but the geometry of motion in a dynamic fabric. In Einstein's universe, the idea of falling took on a completely new meaning. What once seemed like a sign of gravity's power, an apple dropping from a branch, a planet circling a star, became the most natural state of motion possible. In Newton's world, objects fell because they were pulled by a force. In Einstein's, they fell because space-time guided them along its curved geometry. Free fall was not the result of attraction, but the expression of freedom. Imagine an astronaut in orbit around Earth. To the untrained eye, she appears to be floating weightless, drifting effortlessly through space. Yet she is not beyond gravity's reach. At that altitude, the pull of Earth's gravity is only slightly weaker than it is at the surface. What makes her weightless is not the absence of gravity, but her perfect surrender to it. She and her spacecraft are both in continuous free fall, moving along the natural curve of space-time around Earth. They fall toward the planet, but their sideways motion is so fast that the planet's surface curves away beneath them. They never hit the ground because space-time itself carries them around it. This is what Einstein meant when he said that gravity and acceleration are indistinguishable. The sensation of weight we feel on Earth is not the effect of a pull downward, but the result of the ground pushing upward, preventing us from following our natural path through curved space-time. Every moment we stand, walk, or sit, the planet is accelerating upward relative to our free-falling trajectory. The weight pressing through our feet, the pressure on our spine, the fatigue of standing, all of it is the experience of resistance to free fall. When we fall freely, whether in an orbiting spacecraft or during a brief plunge from a height, that resistance vanishes. The feeling of weight disappears because nothing is pushing back against our natural motion. We are no longer held by the geometry, we are moving with it. In those moments, we experience the universe as it truly is, a smooth, silent continuum that carries all things along its curves. Parabolic flights, often called the vomit comet, provide short glimpses of this freedom. A plane climbs sharply, then arcs downward in a controlled fall, following a perfect parabolic path. For 20 seconds at a time, everyone inside floats as though gravity has vanished. In reality, they are all falling together, passengers, plane, and everything else, tracing the same geodesic through space-time. Their apparent weightlessness is proof that gravity is not a force acting on them, but geometry shaping their motion. This same principle governs the orbits of planets, moons, and satellites. Every object circling a larger one is in free fall. It never stops falling, but because space-time is curved, its path closes on itself, forming an orbit. The moon's continuous fall around Earth, Earth's around the Sun, and the Sun's gentle motion through the Milky Way all follow this same rule. None of them are being tugged through emptiness. They are all gliding along the contours of space-time created by the mass and energy of the cosmos. On Earth, we rarely experience this directly because the surface interrupts it. The ground exerts an upward normal force, keeping us from continuing our natural descent through space-time. That upward push is what we interpret as the force of gravity, but it is an illusion born from resistance. Einstein turned Newton's law upside down, literally. Gravity is not what pulls us down. The floor is what pushes us up. This reinterpretation of weight changed more than physics. It altered the human understanding of motion, rest, and reality itself. If free fall is the natural state of motion, then being still on Earth's surface is a constant act of acceleration. Every standing person is, in a sense, an astronaut experiencing the universe from within a resisting frame. Our bodies, our clocks, and our senses all conspire to make this resistance feel like normalcy. Einstein revealed that normalcy is the illusion. Modern experiments confirm this truth with astonishing precision. Instruments called accelerometers, used in spacecraft and smartphones alike, detect acceleration by measuring the force exerted on a small mass inside. When an accelerometer is dropped freely, it reads 0. Not because gravity is absent, but because no resistance acts on it. The same happens aboard the International Space Station. Though it orbits at nearly 28,000 kilometers per hour, its accelerometers read 0 because it is in perfect free fall. The International Space Station is one of the most beautiful demonstrations of general relativity in action. Every piece of it, from the solar panels to the experiments inside, moves along a geodesic path around Earth. The astronauts inside are weightless because they share that same motion. They are not suspended above gravity, but immersed in it, carried by spacetime's curvature like leaves drifting on a vast, invisible current. Free fall also provides an ideal environment for scientific discovery. Experiments conducted in microgravity reveal subtle effects that gravity on Earth hides: the behavior of fluids, the growth of crystals, and even the delicate balance of atomic clocks. In orbit, time flows just slightly faster than it does on Earth's surface, a difference so tiny it can only be measured by precision instruments. Yet it matches Einstein's predictions perfectly. The equality of free fall also ensures that everything, regardless of composition, follows the same path through spacetime. Whether a hammer or a feather, both accelerate identically in the absence of air resistance. This was dramatically demonstrated on the Moon during the Apollo 15 mission, when astronaut David Scott dropped a hammer and a feather side by side. Without air to slow them, both struck the lunar surface simultaneously. Einstein's principle of equivalence, born in the mind of a solitary thinker, was confirmed on another world. To Einstein, this was not merely coincidence, but the signature of geometry itself. If all objects fall the same way, it must be because they are not being pulled by different amounts of force, but are all following the same curved spacetime. The geometry dictates motion, not mass or material. This universality is what makes general relativity so elegant. The entire cosmos obeys one simple rule: move freely and geometry will guide you. The reality of weightlessness, then, is not a suspension of gravity, but its perfection. It is what happens when motion aligns completely with the structure of space-time. Every orbit, every fall, every gliding satellite is the universe's geometry in action. The apple that fell on Newton's head was not pulled. It was released to follow the curve of Earth's space-time. And the ground that stopped it was not the source of force, but the barrier to freedom. In Einstein's world, to fall is to be free, and to stand still is to resist the nature of the universe. The truth of weightlessness reveals the deeper illusion that gravity is not an external pull, but a condition of the geometry through which all things move. To Einstein, this was not a loss of magic, but its return. The universe was not ruled by invisible hands, but shaped by the very structure of existence. And in that structure, every orbit, every fall, and every rise told the same story. The motion of space itself guiding the motion of all within it. But geometry does not only move space, it also bends time. Einstein's understanding of free fall and weightlessness naturally led him to the next question. If geometry could move and guide motion, could it also distort time itself? To him, it was inevitable. In a universe where space and time are woven together, any curvature in one must affect the other. The deeper the gravitational field, the more slowly time must flow. The link between motion, geometry, and the ticking of clocks became one of the most astonishing consequences of general relativity. He had first realized this in his thought experiment of the accelerating elevator. Inside, a beam of light entering from one wall would appear to bend downward as the elevator moved upward. To the observer within, this bending was indistinguishable from what would occur if the elevator were stationary on a planet's surface. But Einstein saw a second effect hidden in the same logic. The light moving upward would lose a tiny amount of energy as it climbed. Because energy and frequency are linked, this meant that the light's color would shift slightly toward the red end of the spectrum. This gravitational redshift implied that time itself must be running differently at different heights. A clock on the floor of the elevator, deeper in the gravitational field, would tick more slowly than one at the ceiling. the same must hold true anywhere gravity exists. Near massive objects, time stretches. Farther away, it runs faster. It was a conclusion as elegant as it was revolutionary. Gravity was not just the curvature of space, but the warping of time. Einstein's prediction was eventually tested with remarkable precision. In 1959, physicists Robert Pound and Glenn Rebka used gamma rays in a tower at Harvard University to measure the change in frequency as light climbed a mere 22 meters against Earth's gravity. The effect was minuscule, a shift of only a few parts in 100 trillion. Yet the experiment confirmed Einstein's prediction exactly. Time flowed measurably slower at the base of the tower than at the top. The implications were profound. Every clock, from an atomic oscillator to a human heartbeat, ticks according to the geometry of space-time around it. The stronger the gravitational field, the slower time passes. For people living on Earth, this effect is imperceptible in daily life. But across the vastness of the cosmos, where gravitational fields vary dramatically, it becomes decisive. Time near a massive star or at the edge of a black hole can run so slowly that years pass there while only seconds pass far away. Even within our solar system, the effect is measurable. Atomic clocks placed on airplanes, mountains, and satellites reveal differences that align perfectly with general relativity. A clock on Earth's surface ticks a few microseconds more slowly each day than one in orbit. This tiny discrepancy, though small, would cripple systems like the Global Positioning System if ignored. GPS satellites, which circle Earth at an altitude of about 20,000 kilometers, must correct their onboard clocks by accounting for both special relativity, because they move rapidly, and general relativity, because they experience weaker gravity. Without these corrections, navigation errors would grow by several kilometers each day. Thus, Einstein's insight, born from thought experiments and mathematics, now guides the technology that helps humanity find its way home. Every time a device locates a position on Earth, it silently pays homage to the curvature of space-time. Gravitational time dilation is more than a technical curiosity. It is a glimpse into the deep structure of reality. It means that the universe does not share a single universal clock. Time is local, sculpted by gravity and motion. There is no absolute now that spans the cosmos. Each observer carries their own flow of time, defined by their position within spacetime's geometry. This realization challenges our most basic intuitions. To the human mind, time seems constant, a steady river flowing from past to future. But in Einstein's universe, that river twists and slows, accelerates and bends, depending on where one stands in the cosmic landscape. Near a black hole, the flow of time nearly stops. For a distant observer, an object falling toward the black hole appears to freeze at the edge, its motion slowed by the extreme curvature of space-time. For the object itself, time continues normally, yet it can never escape the region it has entered. Even light, the fastest entity in existence, is not immune to time's bending. As it climbs away from a massive body, it loses energy, its frequency decreasing. This redshift has been observed not only on Earth, but in the light emitted from white dwarfs, stars so dense that a teaspoon of their material weighs tons. Their gravitational fields are strong enough to stretch light's wavelength significantly before it reaches us. Every photon that escapes their surfaces carries the signature of curved time. The warping of time also means that the universe has no fixed rhythm. The passage of seconds, minutes, and years depends on where they are measured. A day on Earth is different from a day near Jupiter, and both differ from a day aboard a spacecraft drifting between stars. The deeper the curvature, the slower the tempo of reality. These effects, once the realm of abstract mathematics, now define the boundaries of human exploration. Missions to Mars, probes orbiting Jupiter, and deep space observatories all rely on the precise timing that relativity demands. Even tiny errors in accounting for gravitational time dilation can lead to catastrophic navigation mistakes over cosmic distances. The same theory that once explained the fall of an apple now guides spacecraft millions of kilometers from home. Einstein's revelation about time was not only a scientific breakthrough, but a philosophical one. It forced humanity to abandon the comforting illusion of a universal clock. The cosmos does not tick in unison. It hums in a chorus of countless tempos, each defined by gravity and motion. The closer we come to massive objects, the slower our experience of existence becomes. Time itself is part of gravity's illusion. This bending of time completes the picture of gravity as geometry. What we experience as the pull of weight, the curve of motion, and the flow of time are all manifestations of the same fabric, warped by mass and energy. Space bends, time slows, and motion follows the geometry they create. Gravity, once a simple attraction between bodies, is revealed as the structure of existence itself. To stand still on Earth is to resist free fall. To orbit is to surrender to it. And to approach a black hole is to feel time itself unravel. The universe's greatest illusion is that these are different experiences. In truth, they are all the same. The expression of geometry in motion, bending both space and time. Einstein's discovery had explained everything from Mercury's orbit to the ticking of satellites, but it also hinted at something darker. If space-time can bend and stretch, could it also collapse? Could curvature become so extreme that not even light could escape its grip? The answer would lead to one of the most mysterious predictions of general relativity, a place where geometry itself breaks down. But Einstein's curved spacetime explained every test. And then physicists discovered places where it breaks. Einstein had revealed that time and space were malleable, that gravity was not a force, but geometry, and that free fall was the purest form of motion. Yet his own equations hinted at something far stranger, regions where that geometry could become infinitely curved, where spacetime itself could collapse under its own weight. He had uncovered the principles that described such places, but he was hesitant to believe that nature would allow them to exist. The mathematics, however, was undeniable. In 1916, only months after Einstein completed his general theory of relativity, German physicist Karl Schwarzschild found an exact solution to Einstein's equations while serving at the front lines of the First World War. He showed that if enough mass were compressed into a small enough region, space-time around it would curve so sharply that nothing, not even light, could escape. At a certain boundary, the event horizon, all paths would bend inward. Beyond that horizon, the direction of time itself would point inevitably toward collapse. Schwarzschild's discovery marked the birth of the black hole, though that name would not appear for another half-century. Einstein admired Schwarzschild's mathematical precision, but doubted that such an object could exist in reality. To him, it seemed absurd that nature could create a singularity, a place where density becomes infinite and the laws of physics cease to make sense. He believed the equations must break down before reaching such extremes. For decades, he resisted the idea, hoping that some undiscovered principle would prevent complete collapse. But over time, the evidence began to build that his own mathematics was correct. The first clues came from the study of massive stars. When a star like the Sun exhausts its nuclear fuel, it collapses inward until pressure from electrons halts the contraction, forming a white dwarf. But for stars more than a few times the Sun's mass, even that electron pressure cannot stop the fall. Their cores continue to compress, crushing protons and electrons into neutrons. This creates a neutron star, an object so dense that a teaspoon of its material weighs billions of tons. But if the collapsing star is even heavier, no known force can resist gravity's grip. According to Einstein's equations, space-time itself gives way, creating a region where all paths lead inward, and the collapse becomes irreversible. By the mid-20th century, black holes shifted from theoretical curiosities to inevitable predictions. In the 1960s, the work of physicists such as Roger Penrose and Stephen Hawking proved mathematically that once a massive star begins to collapse beyond a certain point, no physical process can halt it. The singularity is not a failure of mathematics, it is a feature of reality. General relativity demanded that such objects must exist. Observations soon caught up with theory. In the 1970s, astronomers discovered Cygnus X1, a binary system emitting intense X-rays. The visible star's motion revealed that it orbited an unseen companion far too massive and compact to be anything but a black hole. Later, other black hole candidates were found, each one confirming that nature does indeed allow space-time to fold in on itself. In 2015, the detection of gravitational waves from merging black holes provided the most direct confirmation of all. The waveform of those ripples matched precisely the predictions of general relativity. The signals describe two black holes spiraling together, merging and settling into a single larger one. Einstein's equations had not only predicted their existence, but the sound of their union across cosmic distances. Perhaps the most striking evidence arrived in 2019 when the Event Horizon Telescope, a network of radio observatories spread across the globe, captured the first image of a black hole's shadow. The target was the supermassive black hole in the galaxy M87, 55 million light-years away. The image revealed a glowing ring of gas surrounding a dark core, precisely matching Einstein's prediction of how light would behave near an event horizon. It was not a photograph in the ordinary sense, but a direct visualization of spacetime's curvature. The darkness at the center was not an object, but the absence of all possible paths outward. What makes black holes so profound is that they strip away every illusion. Inside their boundaries, the distinction between space and time breaks down. The closer an object gets to the event horizon, the more time slows relative to the outside universe. To a distant observer, anything falling toward a black hole seems to freeze at the edge, fading slowly into darkness. For the falling object itself, time continues normally, but its future is sealed. It can only move inward, deeper into spacetime's collapse. In Einstein's framework, nothing inside a black hole feels a pull. Everything within it follows geodesics, the straightest possible paths through the curved spacetime that the mass has created. Gravity, even here, is still geometry, though the geometry has become so extreme that escape is impossible. The concept of force remains absent, only curvature remains. Black holes test the limits of general relativity. Near their centers, the curvature of spacetime becomes infinite, and Einstein's equations no longer provide answers. They predict their own breakdown, a sign that a deeper theory must exist, one that merges relativity with quantum mechanics. Yet even incomplete, general relativity has described every observable property of these cosmic abysses with exquisite precision. For Einstein, who had sought a universe of order and continuity, black holes would have seemed unsettling, places where the smooth geometry of space-time tore itself apart. But for modern science, they are among the most beautiful phenomena in existence. They reveal the full power of Einstein's vision, gravity as geometry, motion as the shape of space-time, and time itself as a participant in that shape. The illusion of gravity has come full circle. The very regions where the force seems strongest are also where its true nature, geometry, is most apparent. There is no pull inside a black hole, no invisible hand dragging matter downward. There is only curvature so steep that all roads lead inward. The fall is free, the geometry complete, the illusion perfect. Beyond the event horizon, the universe as we know it ceases to exist. Space becomes time, and time becomes fate. What lies within remains hidden, perhaps forever. Not because light is swallowed, but because geometry itself turns inward, locking information behind a barrier defined by space-time's own structure. Black holes are the ultimate manifestation of Einstein's discovery. They are places where the distinction between illusion and reality dissolves entirely, where gravity's mask falls away, and the pure geometry of existence stands exposed. But Einstein's theory, as flawless as it seemed, faced a challenger, one that emerged not from the stars, but from the smallest scales of nature, the quantum world. Einstein's revelation that gravity is geometry carried a consequence so astonishing that even he found it unsettling. Gravity could change the flow of time itself. The deeper one stands within a gravitational field, the slower time passes. The ticking of a clock, the rhythm of a heartbeat, the aging of a person, all are affected by the curvature of space-time. Gravity, it turned out, was not only the shape of space, but also the tempo of existence. The idea first emerged from a thought experiment. Imagine, Einstein proposed, a beam of light inside an accelerating elevator. To someone inside, the elevator's floor seems to rise toward the light, making the beam appear to curve downward. Yet to an observer outside, the light travels straight. The two descriptions are indistinguishable, proving that acceleration and gravity are equivalent. But if light changes direction in a gravitational field, Einstein reasoned, then its energy must also change. Light climbing upward against gravity should lose energy, stretching into longer wavelengths, a phenomenon known as gravitational redshift. This shift in frequency implied something profound. Time itself must be running slower, deeper within the gravitational field. For if the light's oscillations slow down, so must the clocks that measure them. It was one of the most radical predictions ever made, that the universe contains no universal clock, no single rhythm that beats everywhere the same. Einstein's idea remained theory until 1959, when physicists Robert Pound and Glenn Rebka tested it in the Jefferson Tower at Harvard University. They sent gamma rays from the bottom of the tower to a detector 22 meters above. As the light climbed upward through Earth's gravitational field, its frequency shifted exactly as Einstein predicted. The effect was minuscule, a change of only a few parts in 100 trillion, but the match was perfect. Time at the bottom of the tower truly moved more slowly than time at the top. In the years that followed, technology transformed this abstract truth into measurable reality. Atomic clocks, capable of detecting differences of a few billionths of a second, confirmed that time passes faster on mountaintops than at sea level. Identical clocks flown around the world returned with tiny discrepancies, each consistent with the predictions of general relativity. The conclusion was inescapable. Gravity stretches time. This effect, known as gravitational time dilation, is no longer just a curiosity of theory. It underlies the technology that guides everyday life. Global positioning satellites orbit Earth at an altitude of about 20,000 kilometers, where gravity is weaker than on the surface. Their onboard clocks tick roughly 45 microseconds faster each day than clocks on Earth. Without correction, GPS positions would drift by several kilometers daily, rendering navigation useless. Every moment, a smartphone determines its location. It does so by silently accounting for Einstein's bending of time. The slowing of time near gravity's depths also shapes the cosmos itself. In the heart of massive stars, where gravity is immense, nuclear reactions burn more slowly because time flows differently. Near black holes, time dilates so severely that an object falling toward the event horizon appears to freeze from an outside perspective. its motion slowed to a crawl by gravity's grip. Yet for the object itself, time continues normally. It experiences nothing unusual as it crosses the horizon. The difference between these two realities is not illusion, but geometry. The effect also reveals itself in light escaping from dense stars. As photons climb out of deep gravitational wells, they lose energy, stretching toward redder colors. This gravitational redshift has been measured from white dwarfs, the collapsed cores of dead stars, and from the surfaces of neutron stars, where gravity is billions of times stronger than Earth's. Every photon that reaches us from these objects carries the mark of slowed time. Einstein's discovery shattered the last remnant of Newton's absolute universe. Time, once thought to flow uniformly everywhere, became relative, intertwined with space, influenced by motion, and shaped by gravity. Every massive object warps not just the path of light, but the passage of time itself. The ticking of clocks, the orbit of planets, and the expansion of the universe are all expressions of the same curvature. Perhaps the most poetic consequence of this realization is its effect on life itself. To live within a gravitational field is to experience time differently than those farther away. Two identical twins, one on Earth and the other aboard a spacecraft orbiting far from any massive body, would age at slightly different rates. The twin near the planet would age more slowly, her every heartbeat stretched by gravity's hand. This is not fiction, but a measurable fact, confirmed by countless experiments and embedded in the equations that guide satellites and spacecraft. Einstein's insight turned gravity into something more profound than force. It became the very fabric of experience, the stage upon which existence unfolds and the metronome by which it keeps time. To walk uphill, to climb a tower, or to rise from Earth's surface is to move forward through time more quickly. To descend into a valley or fall toward a planet is to slow time's flow. The world around us is a gradient of temporal speeds, all synchronized not by absolute clocks, but by geometry. In the deepest sense, this means that the universe does not share a single now. Each point in space-time experiences its own moment, its own tempo, shaped by gravity's strength. The cosmos is not a sequence of events marching forward in unison, but a vast tapestry of moments woven together by curvature. Gravity binds those moments into harmony, creating the illusion of a shared flow of time. Einstein's equations describe this with elegant simplicity. Matter tells space-time how to curve, and space-time tells matter how to move. But hidden within that relationship is something even grander. Time itself obeys the same rule. Mass and energy warp not only the geometry of space, but the rhythm of existence. Through the slowing of clocks and the bending of light, gravity reveals its true identity. It is not a force pulling on objects, but the shape of time and space themselves. The apple falls, the planet orbits, and the clock ticks slowly, not because they are acted upon, but because they follow the contours of space-time. Einstein's curved space-time explained every test, but then physicists discovered places where it breaks. The deeper scientists explored Einstein's equations, the more they realized that space-time could not only bend, it could collapse. The same mathematics that describe the gentle orbit of planets also predicted regions where curvature would grow without limit, where geometry itself would fold inward and consume all that entered. These regions would come to be known as black holes. Einstein himself doubted their existence. In 1916, Karl Schwarzschild found an exact solution to Einstein's field equations, describing the space-time around a spherical mass. The solution revealed a critical boundary: compress enough mass into a small enough space, and the escape velocity would reach the speed of light. Beyond that boundary, not even light could escape. It was a terrifying and beautiful idea, a place where space and time ended. Einstein admired the mathematics, but dismissed the possibility. He believed nature would forbid such extremes, yet the universe disagreed. As stars die, their cores collapse. For smaller stars, electron pressure halts the fall, creating white dwarfs. For heavier stars, neutrons resist the compression, forming neutron stars. But above a certain mass, roughly 3 times the mass of the Sun, no known force can stop the collapse. The star's core shrinks until the curvature of space-time itself becomes infinite. This is the birth of a black hole. Its defining feature is not a surface, but an invisible boundary, the event horizon. To an outside observer, it marks the limit of return. Cross it, and all paths, even those of light, lead inward. For an infalling traveler, the crossing feels ordinary. There is no wall, no flash. Yet the geometry of space-time has already sealed their fate. Inside, all directions curve toward the singularity, the heart of infinite density, where known physics ceases to apply. For decades, black holes were considered mathematical oddities, but the cosmos revealed otherwise. In the 1960s, astronomers discovered Cygnus X1, a bright X-ray source whose motion suggested an unseen massive companion. It emitted no light, but tugged powerfully on a visible star. The only possible explanation was a black hole. Later, entire galaxies were found to harbor supermassive black holes at their centers, some containing billions of solar masses. The violent jets and radiation from quasars, the most luminous objects in the universe, come from matter spiraling into these gravitational abysses, heating to millions of degrees before vanishing. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory detected ripples in space-time from 2 merging black holes over 1 billion light-years away. The signal, lasting less than a second, matched Einstein's predictions exactly. It was the first direct evidence that the geometry of space-time can ripple, and that black holes not only exist, but collide. 4 years later, the Event Horizon Telescope captured the shadow of a black hole at the heart of galaxy M87. The image revealed a glowing ring of light bent by immense curvature around a dark center. The ring was not an object but a photon orbit where light circled the abyss before escaping. The darkness in the middle, the shadow, marked the region from which no light could ever return. Humanity had photographed the geometry of nothingness. In black holes, Einstein's illusion becomes absolute. Gravity, as a force, disappears entirely. There is only motion along space-time's curvature. Matter does not fall because it is pulled. It falls because the geometry directs it inward. The event horizon is not a barrier, but a property of space-time itself. To an outside observer, time near the horizon slows infinitely, freezing the infalling object. To the falling object, time flows normally until the singularity consumes it. The singularity, where curvature becomes infinite, is the limit of Einstein's theory. Here, his equations break down, not because they are wrong, but because they reach the edge of their domain. General relativity describes smooth geometry, but at infinite curvature, that smoothness cannot exist. To describe what happens inside, a new theory is required, one that merges the geometry of relativity with the probabilities of quantum mechanics. In their paradoxes, black holes reveal the future of physics. They are the bridge between Einstein's continuum and the quantum world. They prove that gravity is not just an illusion of force, but an illusion of completeness, that beyond geometry lies something deeper still. But Einstein's theory faces a rival at the smallest scales, the quantum world. Einstein's equations ruled the universe of stars and galaxies, but at the smallest scales, a different set of laws prevailed. Quantum mechanics, born from the study of atoms and light, described a reality governed by uncertainty and probability. It revealed that particles could exist in many states at once. that energy came in discrete packets, and that observation itself shaped what was real. Einstein admired quantum theory's precision, but distrusted its philosophy. He believed nature must be orderly, not random. God does not play dice, he once said, but experiment after experiment proved that the quantum world is indeed probabilistic. Atoms do not follow predictable paths, they explore all possibilities simultaneously. The universe, at its core, is a realm of uncertainty. This worldview clashes with general relativity, where space-time is continuous and deterministic. In relativity, the future is written in geometry. In quantum mechanics, the future is a set of probabilities. When scientists try to combine the two, the mathematics collapses into infinities. Near singularities, like those inside black holes or at the universe's birth, both theories should apply, yet they refuse to coexist. To reconcile them, physicists have explored new frameworks. String theory proposes that the universe's basic building blocks are not particles, but tiny vibrating strings. Their vibrations determine the properties of particles, and one vibration corresponds to the graviton, the quantum carrier of gravity. The theory naturally includes gravity, but only in a universe of 10 or 11 dimensions, most of them hidden from view. Another approach, loop quantum gravity, suggests that space-time itself is quantized, built from discrete loops of geometry. At the smallest scales, space is not smooth but granular, composed of finite units of area and volume. The theory eliminates the infinities that plague relativity and hints that singularities may not truly exist. These attempts share a profound idea. Space-time and gravity may not be fundamental. They might emerge from something deeper, the structure of quantum information. The holographic principle embodies this insight. It states that everything inside a volume of space can be fully described by information on its boundary. The universe, in this view, could be like a vast hologram, where three-dimensional reality arises from two-dimensional data. In 1997, Juan Maldacena discovered a mathematical bridge between these worlds, the ADS-CFT correspondence. It showed that a gravitational theory in curved spacetime could be equivalent to a quantum field theory on its boundary. Geometry and quantum information were two sides of the same reality. If this is true, then Einstein's spacetime is an emergent illusion, a large-scale approximation of the entanglement between quantum systems. Gravity would not be a field or a force, but the result of how information arranges itself. Spacetime, in this sense, is what quantum entanglement feels like when viewed from afar. Einstein's dream of unity lives on in this search. Though he could not accept quantum randomness, the quest for a theory that merges geometry and probability remains his legacy. Somewhere beyond our current understanding lies a framework where space, time, and matter emerge naturally from information, where the illusion of gravity becomes the language of reality itself. Einstein's equations may describe the illusion, but what lies beneath space-time itself? Einstein's discovery transformed physics from a study of forces into a study of form. Gravity, once the invisible hand that guided the cosmos, became a property of geometry, the shape of space-time responding to matter and energy. Yet modern physics suggests that even geometry may not be the foundation of reality. The curvature of space and the flow of time may themselves arise from something more primitive: information. In this emerging view, the universe is not built from things but from relationships, from data that define how energy and matter interact. The geometry of space-time, the motion of planets, and the bending of light all emerge from the underlying patterns of information. Einstein's force was an illusion. Now even his geometry may be another. Physicist Eric Verlinder's theory of emergent gravity offers one glimpse of this future. He proposes that gravity arises from entropy, the universe's tendency toward disorder. As matter moves, It changes the distribution of information, and the resulting imbalance creates what we perceive as gravitational attraction. In this framework, gravity is not fundamental but statistical, the macroscopic expression of microscopic processes. This idea could explain mysteries that puzzle modern cosmology, including the apparent effects of dark matter. If gravity emerges from information, then the extra attraction observed in galaxies might arise naturally from the entropy of space-time rather than from unseen particles. Though still unproven, this approach extends Einstein's logic. What we interpret as a physical force may simply be the geometry of information adjusting toward equilibrium. General relativity remains flawless within its domain. Its equations predict every observed effect: the bending of starlight, the slowing of clocks, the expansion of the universe. But at the edges of knowledge, near singularities, inside black holes, and at the quantum scale, it hints at its own incompleteness. There, geometry gives way to information. Einstein's legacy endures because he replaced mystery with principle. He showed that gravity was not a pull, but a pattern, not a force, but a form. Now, physicists pursue that same elegance one level deeper, seeking the principle that gives rise to geometry itself. Whatever its final form, whether quantum, holographic, or informational, the next great theory will begin where Einstein left off, with the understanding that reality's most powerful forces are illusions born of deeper order. The apple that fell on Newton's head was not tugged downward by an unseen hand. It followed the curvature of space-time, and that curvature may itself have been shaped by the universe's invisible network of information. The apple never fell because it was pulled. It fell because reality's geometry curved its path. Einstein did not destroy gravity. He revealed it as geometry, turning one of nature's greatest forces into one of its most profound illusions. In the end, Einstein's greatest gift was not a set of equations, but a way of seeing, a reminder that nature's deepest truths often hide behind familiar appearances. What began as a question about falling objects became a revelation about the structure of reality itself. He taught humanity that what we call force is only perception, that gravity is not a tug through emptiness, but the shape of existence unfolding in time. And though modern physics now peers beyond even his geometry, toward quantum information, holography, and the idea that space-time itself might be emergent, the spirit of Einstein's vision remains untouched. It is the recognition that order lies beneath chaos, that simplicity hides within complexity, and that the universe, in all its vastness, is governed not by mystery, but by meaning. Gravity was never an external power. It was always the quiet curvature of truth.